2. Relax and think clearly and thoroughly through the problem to the solution. 3. Remember to ask and look for help when unsure, especially if added downtime and catastrophes may be a result of experimentation. When you get to where you don't know what you are doing, call people who do. If you can't get them right away, call others or wait. 4. Don't fret. You don't need this job anyhow if management is asking you to be foolish. Many times, management does not understand the gravity of the situation. Management does not really want to take chances on serious damage, and you must remind them of that. With this in perspective, we go through Plan A while keeping Plan B on the back burner. Phase 480 volts AC is applied to L1, L2, and L3 when the breaker is closed. When coil voltage is applied to the electromagnet, the 480 volts AC is also being applied to T1, T2, and T3, and consequently to the leads of the motor. The motor will turn if the motor is good, and not being asked to work harder than its horsepower rating. One of 3 items is keeping the holding circuit from operating: the connections and wire from terminal 3 to terminal N, the aux contact itself, and the connections and wire from terminal O to terminal 4. One of these can be easily eliminated. The voltage at terminal N should be 120 volts AC whenever the stop switch is not pushed. After confirming 120 volts AC at terminal N, this leaves only the aux contact itself and the connections and wire from terminal O to terminal 4. How could this problem be isolated using a voltmeter? The voltage at terminal O can be supplied from 2 different directions, from the start switch and from the aux contact. When isolating the voltage, one of the paths has to be eliminated. A process of elimination is to disconnect a wire and feedback path from the start switch to the M9 aux contact. This module discusses some of the more complex electronic, electrical, and electromechanical topics that have not been discussed in detail so far. The information learned so far and the information learned in this module shall be used for a case study in Module 6 that troubleshoot a very complex system of many of the components studied. Besides learning about the components used in the complex system for the case study, we'll include components useful in developing your career that will help you understand the applications unique to your industry and job duties. This module discusses and troubleshoots 1. On-off control systems, as well as 3-mode control. 2. Position actuators and lever adjustments. 3. Voltage dividers. 4. Variable speed drives. 5. Digital tachometers and encoders. 6. Signal conditioning. 7. Digital and analog inputs and outputs. 8. Load cells and continuous weigh scales. This is a closed-loop control. This controller is placed in a damper control application. The controller. The photohelic is more than a pressure gauge. It has 2 red needle set point switches that actuate when the black needle passes over the red needles as the black needle fluctuates with the changing pressure. When the low set point is wired to energize the actuator open windings, and the high set point is wired to energize the actuator closed windings, the flow of exhaust gases through the drum can be controlled. The on-off action of this control is considered a simple controller. The more complex controllers, such as a 3-mode PID controller explained later, adjust for the amount of output signal and timing of signal, depending on internal controller adjustments and the controller inputs. Rectifier converter. One of the 3 primary sections of a VFD's main power circuit, and first in terms of power flow. Incoming AC line voltage is rectified to DC voltage in the converter section, which consists of diodes, silicon-controlled rectifiers, SCRs, or insulated gate bipolar transistors, IGBRs, connected in a full-wave bridge configuration. DC bus. The second primary section of a VFD's main power circuit chiefly consists of capacitors that store power rectified by the converter. Inverter. The third and final primary section of a VFD's main power circuit. The inverter section is comprised of IGBTs that create sinusoidal output current using pulsed DC bus voltage or pulse width modulation, PWM. VFDs themselves are sometimes called inverters, as the presence of an inverter section is the primary difference between VFDs and DC drives. Carrier frequency. In PWM-based VFDs, the rate at which output transistors are graded or turned on, usually 2 to 15 kHz. Higher values yield a better current waveform, but more VFD losses. Scale indicator supplies excitation voltage to the load cell, and in turn, the load supplies a signal voltage to the indicator in proportion to the weight applied to it. The diagram shows a 4-wire load cell. The load cell has 2 input wires and 2 output wires. The load cell has a full-scale load rating and a full-scale output sensitivity rating. The maximum load for a load cell is usually equal to 150% of its full-scale rating. The full-scale millivolt output is equal to the excitation voltage multiplied by the full-scale output sensitivity rating. With a 10 volts DC excitation input, a 2 millivolt per volt full-scale sensitivity rating, and a 10-pound full-scale load rating, the output ranges from 0 millivolts DC to 20 millivolts DC, as the applied load ranges from 0 pounds to 10 pounds. Electronics can measure many things. With those measurements, one can be calculated against another. Some signal type need to be converted from one signal type to another. Sometimes alarms should be initiated depending on a signal threshold. In Module 6 case study, a 3-mode controller requires a 420 milliamp input, but the setpoint transmitter may only produce a 0 to 2 kHz signal. Therefore, a frequency to DC transmitter is used to make up the communication gap. Wilkerson, ActionPack, Absolute Process Instruments, etc. develop modules for some of the following functions listed. Please read on for yourself. The burner control is set to automatic and controls smoothly until the mixed temperature probe fails. During a hot stop, the failed thin temperature probe is replaced with a thick, massive temperature probe. Since the replacement temperature probe responds more slowly to temperature changes, the controller is now hunting for its set point by opening and closing the burner position actuator too slowly. This system has so many pluses. The benefits vary depending upon what the job requires. Some jobs require all the dust to be used and returned to the drum mixer at an even flow rate despite the varying dust rates from the baghouse. Some jobs require a certain amount of dust to be returned to the process and the balance to be rejected. Controlling various processes is usually simple when the variables are predictable and consistent. The measuring device is right next to the flow control device, meaning there is hardly any delay from the time the flow control valve is adjusted and the flow rate is measured. This allows for a very smooth and tight control with little or no hunting when material is delivered to the flow control valve consistently. As the challenges grow in the troubleshooting journey, the need to know more about the process is required. Detailed information is provided for this purpose. The thought process of the design engineer is included, so you may have the insight why some things were designed the way they were. This is a good time to download the drawings, reference manuals, and cut sheets. You will need them for research and to refer to when analyzing and isolating the problems. When doing so, you will start connecting more of the dots to the dots you now understand. Each time you read a reference manual, you get more out of it. Up to this point, you learned basic electrical, simple, and increasingly more complex circuits, how to use a test meter safely, and safely troubleshoot relatively complex electrical circuits. These circuits can be meaningless if not incorporated with the physical mechanical world and the world of software. Control systems may control electrically, but getting actual work done is usually mechanical. When performing the work to the best, closed-loop control is normally called upon to get the task done. When doing so, electromechanical devices are required to work as a functioning system. The system we are presenting to study shall be a machine used to introduce a material by weight into a final product accurately and automatically. A series of mechanical devices are required to continuously feed a mechanical signal to a load cell that converts the signal to a tiny electrical analog signal. Another displaying converter reads the signal as a rate of flow and counter of pounds of material passing through the scale. A variable speed conveyor feeds this scale based upon the As the challenges grow in the troubleshooting journey, the need to know more about the process is required. Detailed information is provided for this purpose. As the challenges grow in the troubleshooting journey, the need to know more about the process is required. Detailed information is provided for this purpose. The thought process of the design engineer is included, so you may have the insight why some things were designed the way they were. This is a good time to download the drawings, reference manuals, and cut sheets. You will need them for research and to refer to when analyzing and isolating the problems. When doing so, you will start connecting more of the dots to the dots you now understand. Each time you read a reference manual, you get more out of it. Up to this point, you learned basic electrical, simple, and increasingly more complex circuits, how to use a test meter safely, and safely troubleshoot relatively complex electrical circuits. These circuits can be meaningless if not incorporated with the physical mechanical world and the world of software. Control systems may control electrically, but getting actual work done is usually mechanical. When performing the work to the best, closed-loop control is normally called upon to get the task done. When doing so, electromechanical devices are required to work as a functioning system. The system we are presenting to study shall be a machine used to introduce a material by weight into a final product accurately and automatically. A series of mechanical devices are required to continuously feed a mechanical signal to a load cell that converts the signal to a tiny electrical analog signal. Another displaying converter reads the signal as a rate of flow and counter of pounds of material passing through the scale. A variable speed conveyor feeds this scale based upon a varying master speed command and the required percentage of this material to the overall mix recipe. A blower sucks the fiber material away to the process. The scale indicator, the variable speed drive, and the closed-loop controller all require data to be entered to enable each of them to work as a system. Whether it be software or hardware or the power source, it may take 1,000 things working right to make the machine work right. It only takes one thing to make it not work right. We hope the last module, Advanced Troubleshooting, challenged you and you were successful passing it. Hopefully you passed the beginner troubleshooting. Depending on where you are in your journey, passing this expert troubleshooting module may have to wait for those just beginning the troubleshooting journey. We hope you find this exciting. Fiber feeder feeds cellulose fiber into a mixing drum. 40 to 50 pound fiber bales are placed on the loading platform. The bale casing is removed by the operator. The bale is pushed onto the conveyor by the operator. The conveyor moves the bale into the hopper as required by the hopper level sensor. The remote control monitors and controls the process after the bale feed operator gets the fiber to the hopper. .535 is controlling the flow of material through a continuous weigh scale by varying the speed of an auger. The material continuously weighed will be blended with a product being continuously weighed through a continuous mixer. The controller will be asked to control the material flow through its scale based on the percentage required of the total mix and the flow rate of the total mix. In this particular application, 0.3% fiber will be added to the hot asphalt mix. The asphalt mix rate may vary from 150 to 500 tons per hour. To configure the controller unique to this application, the following parameters are required to be set as such. Remote set point, type 4 to 20 mA from plant rate output, is enabled to recognize the plant tons per hour. PV type, 4 to 20 mA from the flow scale is enabled. Contact 1 shall force the 535 to manual when fiber feeder is shut down. This allows the controller to remember what speed scale auger is to run at when the feeder is restarted in automatic. Consequently, this reduces a lengthy ramping up time and overshoot when the process is restarted at a rate the process was at before shutdown. Analog output, blend control output to control VFD speed. Digital output 1. Alarm relay on to illuminate deviation light when flow scale reading is significantly different than required set point. Digital output 2. Alarm relay on to sound scale being plugged horn. If the material, fiber, being weighed plugs up in the scale for some reason, the auger packs material in and the flow scale reading begins to increase rapidly. This may have been caused by the scale being overfed or the discharge airstream through the blower was not flowing when material was being fed. Material blending. The scale feed auger is variable speed. Its speed is adjusted in the remote control panel, either manually or automatically. The blending mode is selected by pressing the manual button on the 535 controller. Manual mode is selected when the manual button is illuminated red. Automatic mode is selected when the manual button is illuminated white. The automatic flow controller follows the plant rate signal and the percentage of fiber required entered by operator. Mechanical connections are very important from the trolley support through the protrusion rod connected to the load cell and the load cell fixed to the scale body. 7 mechanical connections are made to transfer the material impact to the load cell. When any one of them becomes loose, the load cell signal is being compromised, and so is the accuracy of the scale. This enclosure has 480 volts AC and enough power to warrant an 8-calorie suit. A voltage monitor is wired to the voltage source. Power may be considered to be disconnected once the circuit breaker feeding the panel is disconnected, while observing the once illuminated lights now extinguishing. While using a wireless meter, the technician on the bottom right is troubleshooting inside his power panel. The 3 local keypads, blower, conveyor, and hopper auger, assist with programming from outside of the enclosure and monitoring the VFD status. The scale auger keypad is mounted on the remote control. It is important for the plant operator to know what the status of the scale feed auger is at all times, as well as having capabilities to reverse the motor, reset any faults, vary the speed without using the controller, reprogram parameters, etc. All other VFDs are continuously set at a certain speed. These relays and timers have LEDs that illuminate when the relay coil is energized, or the timer is timing, but do us no good if we are not suited up with the door open. The relays and timers are labeled as listed below as to what happens when their coils are energized. This is a great troubleshooting convenience. Read on for yourself. On and off from the remote control panel without starting augers. This is designed so that the scale can be zeroed under process conditions and the airflow is up to full speed before the augers start. Otherwise, the fiber added by the augers will not be carried away in a slow-moving airstream. The blower is required to stay on after the augers are stopped and the flow of fiber has ceased. This is controlled by the post-purge timer. This added blower runtime is used to clear the line of all fiber before shutting the process down. R2 is the delay on make (BMR) operation. The local remote switch on the local control panel is set to remote. The sequence is started when the operator selects blower on at the remote control panel. Relay R5 is now energized. Timer TR2 is enabled by the closed normally open contact of R5, and the time delay period for TR2 starts. Since TR2 is a delay on make (BMR) timer, its normally open contact remains open during the time delay period. During the time delay period, an auger motor start signal comes in on terminal 6, which enables R6. A normally open contact of R6 closes, which is intended to start the scale auger motor. The scale auger motor does not start since TR2 has not timed out yet, and its normally open contact is still open. When TR2 times out, its normally open contact closes. Due to a bad connection, the scale auger does not start. With R3 active, DC voltage checks are made. The first check is made at R3 terminal 7. The expected good voltage is 0 volts DC. The actual voltage is 24 volts DC. The second check is made at R3 terminal 4. The expected good voltage is 0 volts DC. The actual voltage is 24 volts DC. The third check is made at VFD terminal SN. The expected good voltage is 0 volts DC. The actual voltage is 0 volts DC. Therefore, there is an open circuit in the wire 62 circuit. Wire 62 has fallen off at R3 terminal 4.